James Webb found hundreds of tiny red objects in the young universe. They were too bright, too compact, and far too common. Then, as the universe grew older, almost all of them disappeared. Now Webb has taken the deepest spectrum yet of one of these objects, and found signs of a black hole concealed inside something that behaves almost like the atmosphere of a star. So what were these red dots? Why could astronomers not see the black holes inside them? And where did they all go? This is the search for the black holes that hid inside the first points of light. Astronomers call them little red dots, which may be the most innocent name ever given to a potentially violent class of object. They are so distant that their light began traveling toward us when the universe was still assembling its first mature galaxies. Before Webb, most were simply too faint, too compact, or too red for earlier telescopes to study properly. But after Webb began science operations in 2022, they appeared in field after field. Not one unusual galaxy. A population. One major survey assembled 341 candidates from several Webb observing programs. The exact number depends on how astronomers define and select the objects, but the pattern was unmistakable. Compact sources with a similar, peculiar combination of colors were showing up throughout the early universe. They were especially common during the first 1.5 billion years after the Big Bang. Later, their numbers fell sharply. Something appeared to switch them on. Then something switched them off, stripped away their disguise, or transformed them into objects that no longer met the definition. For a time, however, even the definition was difficult. The dots were selected from light measured through filters, not from close-up photographs. Every one of them remained an unresolved point or a barely extended smudge. Their true structures had to be reconstructed from the information encoded in their light, and that light seemed to tell several different stories at once. When a telescope observes a remote galaxy, it is also looking into the past. Light travels at a finite speed. The farther the source, the younger the universe appears in the image. Cosmic expansion stretches that traveling light. Ultraviolet and visible wavelengths produced by an early galaxy arrive at Webb shifted into the infrared. This stretching is described by redshift. Webb was built for exactly this task. Its segmented mirror collects faint infrared photons, while instruments such as NIRCam separate the sky into images, and NIRSpec divides the light into spectra. An image tells astronomers where an object is and how bright it appears through broad wavelength bands. A spectrum goes further. It spreads the light into a detailed barcode. Each dip and peak can reveal an element, a temperature, an outflow, dense gas, or radiation coming from a hidden energy source. For the little red dots, those barcodes became essential because color alone created an alarming possibility. If all their red light came from stars, some early galaxies appeared to contain far more stellar mass than they should have had time to assemble. In the first Webb surveys, this was sometimes described as a challenge to the standard history of the universe. But an unexpected brightness does not automatically mean cosmology is wrong. It can also mean that the wrong object has been assigned to the light. The crucial question was not merely how bright the dots were. It was what exactly was shining. That question connects the dots to an older mystery. In the present-day universe, the centers of large galaxies often contain supermassive black holes. The Milky Way has Sagittarius, a star about 4 million times the mass of the Sun. Other galaxies contain black holes weighing millions or billions of suns. There are several plausible ways to begin building one. A massive first-generation star can collapse, leaving a black hole seed tens or perhaps hundreds of times the Sun's mass. Dense clusters can drive repeated collisions and mergers. Under special conditions, an enormous cloud of primordial gas may collapse almost directly into a black hole, producing a much heavier seed. But no matter which pathway begins the process, A black hole still needs fuel. Gas falling inward does not simply drop through the event horizon. It usually carries angular momentum and forms a rotating flow. Friction, magnetic fields, compression, and turbulence heat this matter until the region around the black hole can outshine an entire galaxy. That radiation creates resistance. As more gas falls inward, the escaping light pushes outward. The balance between inward gravity and outward radiation pressure is represented by the Eddington limit. It is not a perfectly rigid speed limit. Black holes can exceed it, especially when the accretion flow is thick, uneven, or able to trap radiation. But sustaining extremely rapid growth is difficult. Now place that problem inside the young universe. Astronomers have observed massive black holes when the cosmos was less than a billion years old. In 2026, Webb observations of another little red dot, Able 2744 QSO1, allowed researchers to map gas moving around its center and directly estimate a black hole mass near 50 million suns when the universe was only about 700 million years old. The black hole appeared to outweigh much of the visible galaxy around it. That does not prove every early black hole formed before its galaxy, but it overturns the comfortable assumption that a large galaxy must always be assembled first, with its central black hole growing slowly afterward. The universe had produced enormous black holes remarkably early. Either their seeds were heavy, their feeding episodes were more intense than expected, or astronomers were misreading the masses inferred from their spectra. The little red dots may preserve the missing stage when those possibilities became reality. A little red dot is not identified by red color alone. First, it appears extremely compact. At Webb's resolution, much of its light can come from a region too small to separate cleanly from the surrounding host galaxy. Second, its spectrum often has a distinctive shape. In ultraviolet wavelengths it may look blue, consistent with hot young stars. Move toward visible wavelengths, shifted into infrared by cosmic expansion, and the same source becomes sharply redder. Plot the brightness across wavelength, and the continuum makes a V-shaped turn near the Balmer limit. The Balmer break is produced when hydrogen changes how strongly it absorbs light around a particular energy. In an ordinary galaxy, a pronounced break can be associated with an evolved population of stars. That interpretation would imply that enough stars had already lived long enough to create the feature. But the red dots complicated this familiar explanation. Many showed broad hydrogen emission lines, a classic sign of gas moving in the intense environment around an active black hole. Some displayed absorption that required very dense gas in front of the source. Their host galaxies were often faint. Their black holes appeared strangely massive compared with those hosts. If the red glow came from enormous numbers of stars, the stars seemed to have assembled too quickly. If the dots were ordinary active galactic nuclei, they should often have been loud in X-rays, radio waves, or hot dust emission. Most were not. And if the width of every line represented gas racing in orbit, conventional calculations produced black hole masses that placed further strain on their young host galaxies. Every simple explanation solved one clue and made another harder to understand. The weak X-rays became one of the strongest objections to the black hole interpretation. Matter very close to a feeding black hole can reach extraordinary temperatures. The surrounding corona and innermost flow can release intense X-ray radiation. Yet stacked observations of many little red dots produced far less X-ray emission than expected. Radio observations were quiet as well. That could mean there was no black hole, but it could also mean the black hole was buried. Imagine an intense ultraviolet lamp behind thick walls. If the walls absorb that radiation and release the energy as heat, the missing ultraviolet light does not prove the lamp is switched off. It tells us something about the material around it. The early universe contained compact reservoirs of gas. A rapidly feeding black hole inside one of those reservoirs might not resemble an exposed quasar. Instead, its central accretion flow could be wrapped inside an optically thick cocoon. High-energy photons would be absorbed or scattered before escaping. Their energy would be reprocessed toward longer wavelengths, where Webb is most sensitive. From outside, the envelope could create a smooth glow resembling an enormous stellar atmosphere. Inside, the power source would be a growing black hole. Researchers began calling this configuration a black hole star. The name is deliberately provocative, but it does not mean a black hole has become a star. It means the surrounding gas performs a role similar to an atmosphere. It hides the central engine, filters its radiation, and creates many of the features seen in the spectrum. This model also predicts something subtle. Light attempting to escape through huge numbers of free electrons will be scattered repeatedly. Each interaction shifts the photon's energy and direction slightly. After enough scatterings, a narrow spectral line develops broad wings. That matters because astronomers often estimate black hole mass from line width. In a conventional active nucleus, faster orbiting gas implies stronger gravity and therefore a larger black hole. But if electron scattering contributes much of the width, the gas may not be moving as fast as assumed. The black holes could be smaller than the first calculations suggested. Still massive, but no longer so massive that the standard cosmic timeline must fail. It was an elegant idea. What it needed was an object detailed enough to test it. Glimpse 17,775 was not the original target. Webb was observing the galaxy cluster Abell S1063, searching for extremely faint galaxies and the elusive first generation of stars. The little red dot happened to lie much farther behind the cluster. That accident was extraordinarily useful. Abell S1063 contains so much mass, including dark matter, that it curves spacetime around it. Light from a more distant source follows that distorted geometry. Images are stretched into arcs, duplicated, and magnified. The cluster becomes a natural telescope. Glimpse 17,775 has a redshift of about 3.5. We see it as it existed roughly 1.8 billion years after the Big Bang. Webb observed its spectrum for approximately 30 hours. With the amplification supplied by gravitational lensing, the effective depth was comparable to around 80 hours without the lens. The result was not a vague red curve. It contained more than 40 identifiable emission and absorption features: hydrogen, oxygen, helium, sulfur, and 16 separate ion features, an entire ion forest hidden inside a dot that barely registers in the image. For the first time, astronomers could test the dense cocoon model using several independent pieces of evidence from the same object. The first clue was the shape of the spectral lines. Hydrogen, oxygen, and helium did not fit neatly into a simple model of a rotating gas cloud. The broad wings were better reproduced when electron scattering was included. The preferred model required electron densities of at least roughly 100 million particles per cubic centimeter. This was not a thin veil. It was an environment dense enough to repeatedly reshape the escaping light. Then came the ion forest. The strengths and ratios of 16 ion lines indicated fluorescence. Ion atoms absorbed energetic photons and re-emitted that energy through specific transitions. Certain oxygen features showed related behavior. These lines required a powerful source capable of pumping energy into the surrounding gas. Helium added further clues. Webb detected enhanced emission and absorption associated with dense material around the central source. Some profiles suggested gas flowing through the envelope rather than quietly circling in a conventional broadline region. Individually, none of those clues is a direct photograph of an event horizon. Black holes are identified through their influence on matter and radiation. Together, However, the clues describe a compact, energetic central engine wrapped inside dense, partially ionized gas. That is exactly the environment predicted by the black hole star model. Under the researchers' preferred interpretation, the central black hole in glimpse 17,775 has a mass of around 5 million suns. It may be receiving material at roughly 1.8 times its nominal Eddington rate. Those values are model-dependent. Change the assumed geometry, scattering process, or motion of the gas, and the estimates change. But the direction of the correction is important. Treating every broad line as rapidly orbiting gas can overestimate the black hole mass. For glimpse 17,775, a scattering-based model produces a value about 10 times lower than a simpler fit to the broad line. The dots may not have broken cosmology. They may have exposed a mistake in the way astronomers were reading their light. The same cocoon can explain several mysteries at once. It can hide X-rays. It can broaden lines without requiring impossibly fast orbital motion. It can create a red optical continuum while allowing blue light from nearby young stars to remain visible. And it can provide a compact reservoir of fuel for an intense growth episode. When gas is supplied at a super Eddington rate, some of the radiation can become trapped in the inflowing material. Energy may escape through preferred directions, while dense gas continues to reach the center through others. The result is not unlimited growth. Radiation, winds, magnetic fields, and feedback still remove matter. But short bursts can build black holes more efficiently than a perfectly spherical, steadily radiating model would allow. Recent theoretical work suggests that little red dot phases could involve black holes growing into a range from roughly 100,000 to 10 million solar masses. Their seeds may have begun as remnants of the first stars. They may have formed through runaway collisions in dense clusters. Some could descend from much heavier seeds produced when primordial gas collapsed directly. The spectrum does not yet identify which origin created glimpse 17,775. It may, however, reveal what happened next. The black hole cocoon is a strong interpretation, not a universal verdict. Little red dot is an observational label. It selects objects by compactness and color. Nature is under no obligation to make every object inside that selection physically identical. Some models propose genuinely supermassive stars, objects perhaps 100,000 times the mass of the Sun, surrounded by self-gravitating disks. Such stars would be brief and unstable, but their photospheres could create strong Balmer features and star-like continua. Other models use more conventional active black holes viewed through unusual dust or gas geometries. Compact starbursts may contribute the ultraviolet light. In some dots, the host galaxy may account for more of the observed spectrum than it does in others. Variability creates another test. An exposed accretion disk can change on relatively short timescales. A large, optically thick envelope may smear and delay those changes as photons diffuse outward. Many red dots show surprisingly little rapid variability consistent with a reprocessing cocoon, although this result also depends on cadence and sensitivity. The Balmer break provides a further complication. Glimpse 17,775 has a weaker break than some other members of the population. Combining Webb with earlier Hubble imaging suggests that a substantial host galaxy contributes blue light around it. That does not destroy the cocoon interpretation, but it demonstrates that the surrounding galaxy cannot always be ignored. Then, in August 2026, a far more extreme object sharpened the argument. It is called MOMBH Star 1. Webb observed it at a redshift of 7.76 when the universe was roughly 670 million years old. Through Webb's bluer filters it almost disappeared. At longer infrared wavelengths it returned as an unresolved point. The spectrum showed why. Across the Balmer limit, the brightness fell by more than a factor of 20. The measured break strength was about 7.7. Ordinary dust-free stellar populations are expected to remain below 3. And even an artificial population made entirely of a type stars should stay below 5. For this object, a normal collection of stars was no longer a convincing answer. At the same time, Webb detected extremely broad hydrogen emission, deep hydrogen absorption, and gas densities of at least 1 billion particles per cubic centimeter. The source was smaller than 100 parsecs. A hint of variability suggested it may have brightened by about 30% over 56 days, although the measurements came from different instruments and need confirmation. The researchers tested close to 1 million simplified gas models, their best match placed an accreting black hole inside a column of almost dust-free, turbulent gas. In that model, gas rather than dust makes the object red. This does not prove that the geometry is exact. The authors explicitly described the model as idealized, but it closes an important escape route to the strange red continuum, and the black hole signatures no longer have to come from separate objects. Even more revealing, MOMBH star 1 lies near a young galaxy at the same redshift. The pair may merge in about 100 million years. Add the galaxy's blue ultraviolet light to the black hole's red spectrum, and the combination begins to resemble a typical little red dot. That suggests the label may describe a composite stage, a gas-wrapped central engine plus a forming host galaxy, CORT. While the two are still assembling, the honest conclusion is therefore narrower than the most dramatic headline. Webb has not proved that every little red dot is a black hole star. It has produced powerful evidence that at least some of them contain rapidly feeding black holes inside dense gas cocoons. That is enough to change the story of early black hole growth. And it returns us to the strangest clue. Why are little red dots common early and scarce later? The most likely answer is that they did not literally vanish. Their appearance changed. During the cocoon phase, a young black hole is surrounded by the material that feeds it. Radiation struggles through the envelope. X-rays are absorbed. Broad lines are reshaped. The source appears compact and red. But this configuration cannot last forever. The black hole's radiation and winds can heat or drive away the surrounding gas. Star formation consumes part of the reservoir. Mergers reorganize the galaxy. Outflows open channels through the cocoon. Eventually, high-energy radiation begins escaping. The smooth red glow gives way to a more recognizable active galactic nucleus. Or the supply of gas falls, the accretion rate decreases, and the black hole enters a quieter state. Either way, the object no longer satisfies the color and compactness criteria used to identify a little red dot. The black hole remains. Its disguise is gone. This explanation is plausible, not settled. Astronomers still need to connect early red dots statistically to specific descendants. They need better measurements of host galaxies, cold gas reservoirs, outflows, dust, and central masses. But the disappearance suggests that the red dots are not a collection of permanent exotic objects. They may be snapshots of a transition. For a relatively brief period, young black holes were wrapped inside the material that allowed them to grow. Then they broke through that material and began influencing the galaxies around them in a different way. The next breakthrough will not come from one beautiful image. Webb must collect similarly deep spectra from more little red dots. If electron-scattered line wings, helium absorption, and fluorescent ion repeatedly appear together, the cocoon interpretation will become much harder to avoid. X-ray observatories must test whether the high-energy radiation is truly absorbed. Radio measurements can search for weak jets or compact cause. Balmer can map cold gas and dust in the surrounding galaxies. Repeated Webb observations can measure variability and watch outflows evolve. And natural gravitational lenses will remain essential. Galaxy clusters such as Abell S1063 turn the mass of the universe itself into part of the telescope. The strongest answer available today is both simpler and stranger than the original crisis. At least some little red dots appear to be young, rapidly feeding black holes surrounded by dense cocoons of gas. The cocoons absorb X-rays, scatter spectral lines, and make their central engines glow like objects far more star-like than ordinary quasars. Glimpse 17775 provides the most detailed evidence yet a more than 40 spectral features: electron-scattered line wings, helium signatures, fluorescent oxygen, and a 16-line ion forest. If that interpretation survives, the dots will have answered one of astronomy's largest questions. Supermassive black holes may not always have grown quietly inside galaxies that were already complete. Some may have begun life hidden inside luminous envelopes, feeding rapidly, reshaping their surroundings, and perhaps helping construct the galaxies that later appeared to contain them. A red dot can look like almost nothing, but it may capture the moment a galaxy's future black hole switched on. If you want to follow what Webb discovers when these cocoons begin to break, stay with Nebula Nexus.